Probability distributions. A random variable is a variable typically represented by x that has a single numerical value determined by chance for each outcome of a procedure. A probability distribution is a description that gives the probability for each value of the random variable. It is often expressed in the format of a table, formula, or graph. A discrete random variable has a collection of values that is finite or countable. If there are infinitely many values, the number of values is countable if it is possible to count them individually, such as the number of tosses of a coin before getting heads. A continuous random variable has infinitely many values, and the collection of values is not countable. That is, it is impossible to count the individual items because at least some of them are on a continuous scale, such as body temperature. In this section, we will go over discrete random variables, and in the next section, in chapter 6, we'll cover the continuous random variables. So a probability distribution has three requirements. There's a numerical, not categorical, random variable x, and its number values are associated with corresponding probabilities. The sum of all those probabilities must equal 1, where x assumes all the possible values. And each individual probability is between 0 and 1 for each individual value of the random variable x. Let's consider tossing two coins with the following random variable. X is the number of heads when two coins are tossed. The above x is a random variable because its numerical values depend on chance. And here's a table of the outcomes. So the probability of getting no heads when we toss two coins is 0.25. The probability of getting one head is 0.5, and the probability of getting two heads is 0.25. Let's go over the requirements. The random variable x is a numerical random variable, and its values are associated with probabilities. The values of that random variable were 0, 1, and 2. The sum of all the probabilities is 0.25 plus 0.5 plus 0.25 equals to 1, and each of the values of the random variable, or the probabilities, are between 0 and 1. And so here's the table. Here are three outcomes, 0, 1, and 2. 3 is a finite number, so it satisfies the requirement of being finite. It's a discrete random variable. Probability histogram is similar to a relative frequency histogram, but the vertical scale shows the probabilities instead of the relative frequencies based on actual sample results. So here's the probability histogram for the number of heads when two coins are tossed. A probability distribution can also be in the form of a formula. Consider this formula. Probability of x, and there's the formula there, where x can be 0, 1, or 2. So if you replace x in there with a 0, you get a probability of 0.25. If you replace x with a 1, you get a probability of 0.5. And if you replace x with a 2, you get a probability of 0.25. And those were the same probabilities that we had in the table, so that probabilities in the table could be represented by this formula. Hiring managers were asked to identify the biggest mistakes that job candidates make during an interview, and the table below is based on their responses. Does the table below describe a probability distribution? So let's go ahead and check the requirements. The table violates the first requirement because x is not a numerical random variable. The values of x are categorical data, not numbers. And by that I mean the values that x can take. Inappropriate attire, being late. These are not numbers, these are categorical. It's a categorical variable. The sum of the table also violates the second requirement because the sum of the probabilities, as we see there, is 1.57, where it's supposed to be 1. Because the three requirements are not all satisfied, we conclude the table does not describe a probability distribution. I should mention it does meet the requirement that each probability is between 0 and 1, but it must meet all three requirements. Remember that with a probability distribution, we have a description of a population instead of a sample, so the values of the mean, standard deviation, and variance are parameters, not statistics. And these can be found with the following formulas. Mu is equal to, and shown here, the summation of each value of the random variable times how likely it is, and we add up all those quantities. The variance formula is given here, and there's a second variance formula here. We're going to use StatCrunch to do these calculations. So the expected value of a discrete random variable is denoted by capital E, and is actually the mean of the outcomes. So E equals mu, and E can also be found by evaluating that same formula. So again, the table below that we looked at before, we're going to go ahead and calculate the mean, variance, and the standard deviation. And I'm going to use StatCrunch. So in StatCrunch, I took a blank sheet and I entered in one column the values of x, 0, 1, and 2, and in the second column their probabilities. And then I used the commands calculator, Stat calculator custom, identify the X values, they're in the column label X, the weights, which are the probabilities, and then I hit compute. And here's what it looks like. I get a little graph. Don't worry about the graph. We really don't use that. It shows the mean right here is 1, and there's the standard deviation, 0.707. And then to get the variance, I simply square the standard deviation. 0.707 squared gives me 0.5. So when tossing two coins, the mean number of heads is 1. The variance is 0.5 heads squared, and the standard deviation is 0.7. The expected value for the number of heads when two coins is tossed is 1 head, which is the same as the mean, which means if we were to collect data on a large number of trials with 2 coins, we would expect to get in the long run an average or a mean of 1 head. Groups of adults are randomly selected and arranged in groups of 3. The random variable X is the number in the group who say they would feel comfortable in a self-driving vehicle. Determine whether a probability distribution is given. If it is given, then we'll find the mean and the standard deviation. If it's not a probability distribution, identify the requirements that were not satisfied. So remember the 3 requirements. Is it numerical random variable? And we see that it is. Within the group of 3, we could have 0, 1, 2, or 3 people say they're not comfortable in the self-driving car. All the probabilities add to 1, and if you check them, they do. And each probability is between 0 and 1. So this is a probability distribution. Now we want to find the mean and the standard deviation. So in StatCrunch, this actually came from a homework problem, and so there was a little icon next to the little data table, and I can open this directly in StatCrunch. And I'm going to use the command stat calculator custom. I'm going to identify X and the weights P of X and then compute. And so here's my output. So my mean is 0.862 and my standard deviation is 0.782. And if I wanted to find the variance, I would square the standard deviation. Identifying significant results with the range rule of thumb. Remember, we worked on this before. Significantly low values are 2 standard deviations below the mean or lower. Significantly high values are 2 standard deviations above the mean or higher. Values that are not significant are between those 2 boundaries, as shown in the diagram on the screen. We found when tossing 2 heads, the mean was 1 and the standard deviation was 0.7. Use those results in the range rule of thumb to determine whether 2 heads is a significantly high number of heads. So I'm going to go ahead and find on the high side, I'm going to take the mean of 1 and add 2 standard deviations, and I get 2.4. So statistically high numbers of heads would be 2.4 and above. Our observation of 2 heads would not be a significantly high number because it's not greater than 2.4. And again, X successes among N trials is a significantly high number if the probability of X or more is 0.05 or less. And this is what we looked at before. And significantly low is going to be if we have X successes among the trials, significantly low if that probability is 0.05 or less. If under a given assumption, the probability of a particular outcome is very small and the outcome occurs significantly less than or significantly greater than we expect with that assumption, we conclude the assumption is probably not correct. The table describes results from groups of 8 births from 8 different sets of parents. The random variable X represents the number of girls among the 8 children. Find the probability of getting exactly 7 girls and 8 births. So we just read that right off of the table. Right here we see the probability of 7 births is 0.031. Find the probability of getting 7 or more. 7 or more would be 7 or 8, so I've gone ahead and added these 2 probabilities together and I get 0.035. Which probability is relevant for determining whether 7 is a significantly high number of girls and 8 births? And to do that, we're actually going to use the probability of 7 or more to make this determination. Remember, our cut point was 0.05. So is 7 a significantly high number of girls in 8 births? And yes, it is, because the probability is less than 0.05. And be sure to watch the StatCrunch video for this section. Here is a link to that video, and it's also located in the Unit 3 module in My Courses.